All right, we started section 4.3 last time, and we looked at rules of logarithms. In particular, there was a few that we talked about. One of them was this inverse idea of being able to see inverse operations counteracting one another. And so I likened it to like multiplication and division counteracting each other. Exponents and logs counteract each other in much the same way. And then the three that are the most prominently displayed throughout this section are the product, quotient, and power rule. So the product rule takes the logs of something that's a product and it separates it out as the addition of logs. The quotient rule takes something that looks like a quotient and it separates it out with subtraction of logs. And then the power rule takes an exponent on the inside of a log and it makes it a coefficient. And not only can you sort of bring things out, sort of flesh them out and make them long, which is what we did last time, you can also condense them and mush them back in together into a single one. Maybe that's the one we did last time. We did the single one. So we did the ones where we combined them and consolidated them all back into a single log expression last time. So what we're going to do today then is we're going to actually expand them out. So the directions will look something like this. Rewrite as a sum or difference of multiple logarithms. So when you're done with the problems in these section, you should not have any multiplication, division, or powers inside of a log. That's really what you're looking for, with maybe a bit of exception, but I'll show you when that happens if we see it come up. So in particular, on part A, you see that there is addition. There's no property that separates addition, by the way. There was nothing over there. So there is addition on our problem, but I can't fix that. But there's also division. So the fact that there's division means that I have the ability to separate my logs. So if I have division, how will my logs separate? As subtraction. So my log, whatever it is to begin with, this one's a natural log, will stay a natural log. The entire numerator will be written inside, so a plus b. And then it's subtraction of the natural log of the entire denominator, which is a. And as much as it would be like great if there were some way to separate the a plus b inside of the log, there's not. You have to stop right there. So this is the most expanded form of this logarithmic expression that we can have. Part B starts out much the same, right? I see a quotient. I can separate it out with the quotient rule, so that's where we'll start. So this one is actually a common log, just log to the of 3 to the negative x, and it would be minus the log of 4. Okay, is everybody good with that so far? That's the same thing we did in the last one. However, I'm not done on this one, and the reason I'm not done is because I have an exponent here that I can actually use another property to change. So what can I do with that exponent in order to expand my logarithm? You can put it in front. It's a power rule. So anything that has an exponent, like number 4 on here, is allowed to move into the coefficient location in front. So this negative x will come down here in front of the log. So negative x log 3 minus log 4. Is that good? All right, I mentioned something like letter C last time. I have multiple things in the denominator, right? I mentioned it from the perspective of how do we consolidate them back together. Well, we have the same expanding them out process here. So the reality is that anything that's in the numerator gets separated with addition, and anything in the denominator gets separated with subtraction. So you can do this all in one step, and I'll show it in 2 steps in a moment just to sort of verify to you that it really does work. So this is log base 2 of 5, and then I can do minus the log base 2 of 2 minus the log base 2 of y. And the reason that I'm allowed to do that, even though the 2 and the y are multiplied, which would indicate that we're adding, is that what we're really doing here, if I wrote it out sort of longhand, is that I'd have a step like this, right, where the denominator became the minus log base 2 of 2y. And then I'd separate out this, so it would be log base 2 of 2 plus log base 2 of y. And do you see how that negative would distribute through? Yeah. So it will always happen that way. The negative will distribute through any multiplication that's happening in my denominator. And so since that's the case, it's simple enough to go ahead and do it to begin with and say that this is minus log base 2 of y. Now there's actually an interesting piece happening here that we also need to recognize before we get too far away. It almost looks like it's done. It looks a lot like part B, right? I have multiple things. They're all separated. There's no exponents. There's no multiplication or division. I mean, all that looks really good. But I have a matching base and interior of a log. This is log base 2 of 2. Okay, so log base 2 of 2 is the value 1. We encountered that in a particular lesson. I think it was in 4.2. So log base 2 of 2 will equal 1, and I need to adjust for that. I'll remind you why in just a second, since that's been a few days. Log base 2 of 5 minus 1 minus log base 2 of y. So again, the reason that log base 2 of 2 is equal to 1, well, there's the one that's in this lesson easily is that this is 2 to the 1. And back over here at the very beginning, that one right there, it tells us that if we have log base a of a, it's right here, that it just equals the exponent 1. So that's one way to justify it or to think about it. This is equal to 1 because of the exponent 1. The other way to think about it is that you can talk about the fact that log base 2 of 2 equals some random dummy variable like we've done before. And if we draw a scorpion tail around, we get 2 to the x equals 2 to the 1, and x in fact equals 1. So the whole expression, which was equal to x, is equal to 1. So multiple perspectives of why that works, but it will work every time. Okay, so sort of by accident, we found out last time that 2 of you have calculators that allow you to put bases in that are not 10 and e, which is very cool. And I made mention of the fact that most of you don't have that capability, but I was going to show you how you can manipulate your calculator to allow you to do it anyway. That's what this is. This is called a change of base formula. So the change of base formula says that if you have log base a of m, okay, and we're looking like a and m are, in particular, they're numbers so that we can utilize our calculator to do this, but it would be true if they were letters or variables as well. This is equal to the log of m divided by the log of a. Okay? Now, that's not the same thing as any of the properties we've had before. This is a single log expression with a single base and a single interior. And it is able to be rewritten as the division of logs. So if we were wanting to find out a decimal approximation for log base 3 of 4.78 using a calculator that doesn't have this capability, in particular, if you're working on a problem like this, it'll say use the change base formula. So even those of you who have the ability to put in a different base, you're still going to show that part of putting this in. So what you're going to do is you're going to rewrite this as log of the interior first, 4.78, divided by the log of the base, which is it's 3 on this one, base 3. So this is what the change of base formula enacts. It enacts this formula, right? Like we've got these pieces in there. And then your calculator is able to do this regardless of the calculator now that you have, if it's scientific or higher. So log of 4.78, you can press enter if you wish, and then divide by the log of 3. And I have 4 decimal points written in my notes, so we'll go with 4 decimal points. I have a feeling that must be because the directions are going to tell you 4. But whatever the directions tell you, that's what we're going to use. So we'll use 4 decimals for what we're working with right now. So this is actually, and it's an approximation, I should write that, 1.4240. Now, Part B does not have that form, but it's definitely in a form that's not user-friendly right now as well. So normally when we have bases, or in exponential form, we have a base on one side, this 0.23 to the x, we want both sides to have the same base. 0.23 is not a very friendly base. Agreed? It's not. And I can't solve for x easily because x is in an exponent location. So since I can't put it in exponential form where it's like 2 to the 5 equals 2 to the 7, I can't do anything like that, right? I don't have the ability to do that. And I can't get that x out in any other way. I'm going to use a scorpion tail to rewrite. So we're going to circle, whoops, sorry about that. We're going to circle the point 23, and draw our arrow around. So this is log base 0.23 of 18.4 equals x. Okay, just following our tail all the way around, we get this form. Now that it's in this form, I can use the change of base formula that we just learned. I can rewrite this now as the log of the interior, which is the 18.4, divided by the log of the base, which is 0.23. So if I do log of 18.4 divided by log of 0.23, and we'll use 4 decimals still, I have negative 1.9816. Okay, is that all right? Okay, we have one more of this variety. I'm sorry, 2 more. I apologize. Looks like 1 more on my notes, but it's definitely 2. All right, so what can I do on part C to solve this? What would you do first? Scorpion tail would be great. So we're going to circle our base and draw our arrow around. It always lands on the exponent. So this becomes log of that base, 1.025, of the 3 on the other side equals 12t. Now what's different about this one than the last ones we did? What's that? The variable isn't alone. You're right. There's a 12t on the right-hand side. So how are we going to get the variable alone? Yeah, you're just going to divide by 12. So whatever we get from this log change of base formula stuff, we're going to divide it by 12 at the end of the process. So I have t equals, we will rewrite this piece with logs. So I have log of 3 divided by log of 1.025. And once I hit the enter on my calculator and get that value, then I'm going to divide it all by 12. I know that doesn't look very nice, but our calculator is doing all the work, so it really doesn't need to look nice. So if I have log of 3 divided by log of 1.025, I'm getting something like 44. Do you guys have 44 or thereabouts? Good. And then divide that by 12, and I will have 3.7076. Any questions on that one? Okay, so D is actually already in log form, but it's not in a form that's helpful either because the variable is embedded as a base. All right, so this is one that we haven't talked about what to deal with yet, but scorpion tail is the only real option we have. We've got to get that base in a location where I can set it equal to something and solve, and there's no way I can do that if it's embedded inside of that location. So I am still going to rewrite with a scorpion tail, but this time I'm starting with a log expression. So I'm turning it into an exponential. So be x raised to the 2.3 power equals 12.33. And it looks weird, but let me think with you for just a second if it looked a little bit cleaner. What if at that point it didn't say x to the 2.3, it just said x squared equals 12.33? What would you do? You'd square root, right? I mean, that's the inverse of a square, is you would square root. Well, I mean, basically we're going to take the 2.3 as the index root. That's what we're going to do. And your calculator may be able to do that really nicely, but there might be a little bit easier of a version to do instead. So I'm going to show you that option. So, I mean, in theory, you maybe could do this, right? Your calculator might be able to compensate and do that just fine. That would be one option. So let me write that in as an option because there's nothing wrong with it. But not all calculators support that and being able to do that 2.3 there. So another option, if yours doesn't do that, is since it's raised to the 2.3, we can raise it to the fraction that's its reciprocal, 1 over 2.3. So 12.33 raised to the power 1 over 2.3. And that would be another way of doing it. Either way's fine. Both of them are perfectly fine. It just kind of depends on what your technology allows you to do. You got to have technology in this section, right? Like you're going to need a calculator, scientific at least. So if you don't own one, don't have one, beg, borrow, and plead somebody to let you borrow it for a little bit because you don't need it forever in this class. But there are certain sections where it's absolutely crucial, and this is one of them. So if we raise this 12.33 to the power 1 over 2.3, if you're putting it into your calculator, it may need you to do this, where you put the 1 over 2.3 in parentheses like so. That's how my calculator forces me to enter it in order to understand the order of operations properly. And I get, what's my variable x? X is equal to 2.9808. Any questions on that?